Hi. In last lesson, we learned how to use the simplex method to solve a linear programming problem. And we showed two examples. One, we solved in graphical method, and another one, we solved manually. Today, we are going to show another example, which are slightly different. We needed to tune up our simplex method and use the two-phase method to solve it. And then we're going to learn how to solve the linear programming problem manually by MATLAB. That means we're not going to use the command LINPORG. Instead, we do it step by step. Finally, we're going to look the sensitivity analysis in graphic method. So let's start from a new example, see the difference from the example we had in last lesson. Well, there is a small milk company supplies milk from two warehouses. One in Buffalo, New York, another one in Williamsport. And the capacity of the two warehouses are 2,000 gallons and 1,600 gallons per day. The company need to deliver the milk every day to 3 different cities. One is Rochester, another one Syracuse, and the third one, all the leftover, goes to New York City. Well, now you remember the story. You have 2 warehouses and deliver the milk to 3 different cities. And the price, the cost of delivering are given in this table. There's 6 different routes. And we look at the price here. Well, too much information for you to remember. So the best way to digest the information is to draw a simple diagram like this. Once the complexity level passes a certain stage. So the 2 warehouses is Buffalo, New York, and Williamsport. And the 3 cities are Rochester, Syracuse, and New York. The capacity of Buffalo is 2,000, Williamsport 1,600. In Rochester, it needs 800 gallons per day, and Syracuse needs 440 gallons per day. And the total is 3,600, then the leftover is 1,360. This all goes to New York. Well, the 6th price tag, I put it here, from Buffalo to Rochester is 4.2 cents, and Buffalo to Syracuse is 4.5, and the price to New York is 6 cents per gallon. So what is the goal? The goal is to send in the right number of gallons to each city, satisfy all the conditions, or we call it requirements, or say constraints, but the cheapest in cost. So we need to minimize the cost. That's a very typical logistic problem. Think about those truck companies like J.B. Hunt and Walmart. They build warehouses, they deliver to all these retail stores. How much logistic, how much more complicated than this. But they all have the same flavor. The flavor, you need to minimize the cost. So if you're good in this, you have a job, probably Walmart will hire you. Anyway, let's formulate the problem. Let's assume we send X gallons from Buffalo to Rochester, and the Y, number of gallons from Buffalo to Syracuse. So in the diagram, this is X and this is Y. So automatically, you can figure out from Williamsport to Rochester should be 800 minus X. From Buffalo to Syracuse should be 1440 minus Y. And then you can figure out all this to New York by just do the calculation. So we have 800 minus X from Williamsburg to Rochester. From Williamsport to Syracuse is this. So what about from Williamsport to New York City? Then it's going to be 600 minus 800 minus X, and minus 1400 minus Y. And then, of course, from Williamsport to New York must be positive. You cannot send the negative gallon for milk. Okay, then we figured out the numbers. The next step, we need to consider the cost. So 4.2, that's from Buffalo to Rochester. 4.5, that's from Buffalo to Syracuse. And this is to Williamsport to Rochester, and the Williamsport to Syracuse, and these two are the cost delivered the rest to New York. So the total cost after you add all the number, that equals 1900 120 minus 1.4x minus y. It's pretty simple linear function. So what is the constraint? The constraint, of course, in Buffalo, you only get 2,000 of milk. The x plus y obvious, less than 2,000. The interesting constraint is the second one. The x plus y must be greater than 1,600. Let's see where it comes from. You know this, if you minus that 16 minus 800 minus 440, that equal negative 640. And when you reduce, this is x plus y minus 640 greater than 0. And that one, you got a lower limit. So unless you deliver this much, x plus y bigger than 640 from Buffalo, the Rochester won't have enough to supply the total number 1360 to New York. So that is a lower limit, a lower boundary you have. So the real difference of this example from the two examples we had in last lesson is this second constraint. We have a lower limit or lower boundary instead of all upper boundaries, upper limits, like example before. And then we have two more constraints. That's x and y cannot exceed what the Buffalo and Rochester need. So total I have 4 constraints. Let's try to add the slack variables to change in equation to equation as we did before. The first one is easy. You add an S1, which is positive, as a slack variable, and then you can make the upper limit to a tight limit. And that is called the slack. But the second, we said you really get a lower limit. You want the x plus y bigger than 640. Of course, you cannot add another positive number to make it equal. You have to subtract another positive number s2 to make it the 640. That minus is the single difference make the previous method break. So it does not work with this one-phase simplex method. Well, we really don't have a new problem, but it's a similar problem with a different setting. We don't need a new tool, but we need to tune our tool a little bit today. Let's observe the solution first. Because the question is so simple, we can draw a graphic solution again. Let's identify the 4 equations. One is the T1 is this line. The x plus y less than 2000. And the G2, that's the lower limit, is going that way. The G2 is x plus y greater than 640. See the 640? The third one is this. The x must be greater than 0, less than 800. That's this one. And then we have another one. The y must less than 1440. This is this line. Okay, then let's erase this piece we don't need. And erase this a little bit. So our feasible domain is this polygon. So we have A, B, C, D, E, F. 6 extreme points. So graphically, the objective function is right here. 1900 120. It's 920 minus 1.4x minus y. And the slope you can see is this. So we move parallelly. So when we say we move parallelly, it means you can move up. When you move up, as long as your point is in the physical domain, you get a solution. But what we need is a maximum solution. We need to minimize, actually it's a minimum solution, minimize this number. So when you move around, you're going to see you move to this point. Well, then you have a line like this. That will give you the minimum. And we calculate this number. So what is this number? Let's see. We know the x is 800 because it's this line. That's the G3. And the meet the G1. The G1 is x plus y equals 2000. And then you get the y equals 1200. X get 800. Then plug into this equation. Minus 1.4 times 800 minus 1200, and then the result is 16,800 in cents. And then that's $168. You get the solution graphically. All you need is move this blue line and simulate it. By the way, we have the graphical program posted on the blackboard you can use.